Up to this point, everything in modules 1 to 6 had one objective: maximize flow, increase rate, improve productivity, create pathways. That objective no longer applies. Hydrogen storage is not production engineering. It is containment engineering. Hydrogen behaves very differently from the fluids you are used to. It moves faster than any reservoir fluid. It rises. It diffuses. It escapes easily. And the system does not remain stable. Containment degrades over time. With every injection and production cycle, the reservoir changes. The seal changes. The system evolves. This changes how you must think. You do not maximize flow. You control it. You limit it. You stabilize the system. Final principle. If you treat hydrogen storage like a production problem, you will lose containment. Hydrogen is difficult to store for a simple reason. All of its properties work against containment at the same time. First, hydrogen has very high mobility. It moves faster than any reservoir fluid. It diffuses through the pore system and even through the seal. The result is important. Even when you do not see visible leakage, hydrogen can still migrate and reduce the amount you can recover. Second, hydrogen has very low density. It rises naturally. Buoyancy drives it upward continuously. This means containment is always under stress. Third, hydrogen has low viscosity. It flows easily and follows the highest permeability pathways. As a result, flow becomes unstable and difficult to control. When you combine these effects, diffusion, buoyancy, and flow all act together. Hydrogen does not stay where you put it. There is another critical point. The system does not remain constant. With every injection and production cycle, the reservoir changes. The seal changes. Containment degrades over time. This creates a very clear engineering challenge. You must maintain containment, control injectivity, and prevent storage loss. Loss can occur through leakage, through diffusion, through mixing, and through chemical reactions. The storage system also matters. Salt caverns provide strong containment and limited interaction. Depleted reservoirs are well understood, but they are reactive and evolve over time. Saline aquifers offer large capacity, but come with higher uncertainty. Final rule: storage integrity depends on the seal, and the seal changes over time. There is a critical difference you must understand. Hydrogen is not carbon dioxide. Carbon dioxide tends to stabilize in the reservoir. Hydrogen does not. Hydrogen has higher mobility. It diffuses faster and spreads beyond the injection zone. As a result, the plume is unstable. Its position cannot be maintained. Hydrogen also has lower viscosity. It flows easily and follows the dominant flow paths. This makes the injection profile difficult to control. In addition, hydrogen has lower density. It rises continuously due to buoyancy. This drives it upward toward the caprock. When you combine these effects, flow, diffusion, and buoyancy all act together. The plume does not remain fixed. It expands, moves, and redistributes over time. Even if there is no visible leakage, containment still weakens. There is another important point. The system continues to change. Mixing alters the fluid composition. Diffusion reduces the amount you can recover. Repeated cycling changes the reservoir structure and the behaviour of the seal. This leads to one key principle. Hydrogen does not stay where you inject it. That changes the role of stimulation. Stimulation is not about increasing flow. It is about controlling movement. You must improve injectivity without destabilizing the system. In practice, this means three conditions must always be satisfied. Allow hydrogen to enter the reservoir, maintain containment, and avoid creating any leakage pathways. Final rule: do not maximize flow. Control it, because once flow is uncontrolled, it becomes loss. Now we move to the control mindset. Stimulation is not a solution. It is a decision that carries risk. Every intervention changes the system. The question is not, can we improve flow? The question is, what will this change? There is a clear hierarchy of intervention. First, near wellbore cleanup. This removes damage close to the well. without changing the formation or the seal. This is controlled. This is the safest option. The rule is simple. Start here. If injectivity is restored, stop. Second, matrix acidizing. Now you begin to interact with the formation. The level of risk increases. The acid must remain local, and the reaction must stay controlled. The objective is to restore the original behaviour, not to extend beyond the damage zone, because once you extend beyond that zone, you lose control of the system. Third, hydraulic fracturing. This is not a routine tool in hydrogen storage. It is a last resort. Fracturing creates new pathways. If a fracture reaches the caprock, containment can be lost, and that loss is irreversible. The rule here is strict. Do not fracture unless containment is certain. If there is any uncertainty, do not proceed. Now put it all together. More intervention does not give you more control. It increases uncertainty. Final principle. Minimal intervention provides maximum control. Once you disturb the system, you lose predictability. Hydrogen storage is not exposed to a single risk. Multiple risks act at the same time. The first risk is leakage. Hydrogen can migrate through microfractures and weak zones in the seal. This leads to loss of stored hydrogen and potential safety exposure. There is an important extension to this. Leakage is not only structural. Hydrogen can also escape through diffusion, even when there is no visible damage. The second risk is chemical and microbial activity. Hydrogen can react or be consumed, forming other gases. This reduces the stored volume and changes the reservoir over time. In practice, this means what you inject is not exactly what you produce. The third risk is material degradation. Hydrogen can enter steel and weaken it gradually. This leads to loss of well integrity over time. These risks do not occur separately. Flow behaviour, chemical reactions, and material degradation all interact continuously. Control is achieved by operating within limits. Pressure must remain controlled. If pressure exceeds safe limits, the seal can be damaged. Fractures must remain contained. Uncontrolled fracture growth creates leakage pathways. Monitoring must also be continuous. You need to detect changes before they become failures. Final rule. Stay within the operating limits at all times, because once those limits are exceeded, the system cannot be fully recovered. Now we move from theory to real decisions. Consider a practical case. A depleted reservoir is selected for hydrogen storage, but injectivity is limited. The approach is simple, but disciplined. Start with near wellbore cleanup. Remove the damage close to the well. If injectivity improves, stop there. There is no need to go further. If it does not improve, apply a limited acid treatment. Keep the reaction controlled. Keep the treatment local. Throughout the process, pressure must remain within limits, and the system must be continuously monitored. If this is done correctly, injectivity improves, containment is preserved, and the system remains stable. The lesson is clear. Minimal intervention provides maximum control. Now consider the failure case. Hydraulic fracturing is applied aggressively, without full certainty about containment. A fracture connects to a weak zone. Hydrogen begins to move upward. Storage is lost. Not partially, permanently. This is not a performance issue. It is the loss of the system itself. Once a pathway is created, it cannot be reversed. This leads to a simple decision framework. First question: is injectivity already sufficient? If it is, do nothing. Second, can the problem be solved by removing damage? If yes, use cleanup or carefully controlled acidizing. Third, is fracturing truly safe? Only proceed if containment is fully certain. If there is any doubt, do not proceed. Final rule. Containment governs every decision. If containment is at risk, you do not act. Now step back and look at the system as a whole. Hydrogen is fundamentally different from carbon dioxide. Carbon dioxide tends to stabilize in the reservoir. Hydrogen does not. Carbon dioxide is denser and tends to remain trapped. Hydrogen is lighter, rises upward, and continues to move. Carbon dioxide benefits from natural trapping mechanisms. Hydrogen does not have those advantages. The result is clear. Over time, carbon dioxide becomes more stable. Hydrogen becomes harder to control. This defines the engineering reality. Hydrogen storage is not a passive system. It requires continuous control. Containment is not something you achieve once. It must be maintained over time. Now consider a simple comparison. Two operators face the same problem. Low injectivity. The first operator increases the treatment intensity. More fluid, more pressure, repeated designs. The outcome is predictable. The system becomes less stable. Containment risk increases. Failure becomes more likely. The second operator takes a different approach. Instead of reacting, the problem is diagnosed. Cleanup is performed first. If needed, a controlled acid treatment is applied. The system is monitored throughout. The outcome is different. Injectivity improves. Containment is preserved. The system remains stable. The difference is not experience or equipment. It is method. One approach increases intensity. The other controls the system. This leads to a final rule. If you repeat a treatment without understanding the cause, you will repeat the failure. Final principle. Containment governs every decision. Once control is lost, performance no longer matters. Now bring everything together. Start with the fundamentals. Hydrogen is the most difficult fluid to store. It moves quickly. It rises. And it diffuses through the system. The main challenge is not flow. It is containment. High mobility drives the risk. Hydrogen can move through microfractures and even diffuse through the seal over time. This means containment is always under pressure. Because of this, every intervention must be judged differently. Any action must answer one question. Will this create a leakage pathway? If the answer is yes, you do not proceed. Acidizing has a limited role. It is used to restore the system, not to extend it or change it. Once the treatment extends beyond the damage zone, control is lost. Hydraulic fracturing carries much higher risk. Fractures create new pathways. If those pathways connect to the seal, containment can be lost. And that loss is permanent. Control depends on operating within limits. Pressure must stay within a safe range. Monitoring must remain continuous. In practice, minimal intervention provides maximum control. There is one final reality to keep in mind. Hydrogen systems are not static. They evolve over time. Containment becomes more challenging. With each cycle. Final principle. You do not manage hydrogen. By doing more, you manage it. By controlling what you do. Now close the system. Everything comes back to one idea. Hydrogen does not stay where you inject it. And the system does not remain constant. This changes everything. You do not maximize flow. You control it. Now consider two approaches. One pushes the system, increases rate, repeats the same design. The result is loss of control and increasing risk. The other controls the system, diagnoses first, limits intervention, protects containment. The result is stability and predictable performance. The difference is not knowledge. It is discipline. Final principle. You control hydrogen by choosing what not to do. Final line. Control the system, or the system controls the outcome.